Well, it's a little bit noisy, but I hope you hear it all. And thank you, everybody, for coming at such unusual time for Moscow seminar. But this is also one of the way to beat city jams, traffic jams. So our conference already contributed to solution of Moscow transportation problems, and also my special thanks to organizing committee who set it the time of this talk at 4 o'clock Vladivostok time, which suits me the best. Actually, we all see the lot of research activities in major scientific centers of Russia around transportation problems. Of course, Moscow is probably leading in this area, but also there are active groups in St. Petersburg, Ekaterinburg, Perm, Nizhny Novgorod, Irkutsk, and of course Vladivostok, maybe on much smaller scale. But transportation problems of Russia goes far beyond the so-called third transportation ring of Moscow. If you look at the country as a whole, you may find a lot of regional transportation problems, especially in the eastern part of the country, which is still maybe considered as undeveloped. And one of the way to develop these territories is, of course, to develop transportation infrastructure. As the most probably famous example you can recall is Transsib itself, which actually created pushed forward very much the development in Siberia and Far East. And so we also we started mainly with the city transportation problems in Vladivostok, which is one of, well, according to statistics, it's the most automobilized city in Russia, with about 600 cars per 1,000 people in the city. So it's quite common now to have 2 cars in the family. So it's and combined with the very difficult or problematic relief of the city, which is highly mountainous, and also it is located on quite narrow peninsula. So it creates a lot of transportation problems there. But it happened that last year we were invited to take part in one interesting problem on the regional scale. It was the development of transportation model for Irkutsk district. That's an area. Of course, Russians all know where Irkutsk is, but for the benefit of those who doesn't know, it's an area west of Baikal, and it's quite important transportation link between far eastern part of the country and European and west and eastern Siberia. By some miracle, administrative miracle, the head of Irkutsk Research Scientific Center in Irkutsk managed to convince local administration that they need transportation model for the area. And so the number of research groups were organized to work on it. And one of them was our small company, which dealt with mathematical aspects of this modeling. The rest of the team was basically people from specific transportation areas, rail, cars, and river, I don't know if it's river transportation, and they were basically fact-providing groups with which we try to collaborate more or less successfully to create some mathematical foundations for this work. And of course, it was done in a typical Russian way, I must say. So the project officially started end of September, and in November, December, we had to write the final report for the whole thing. So we're not quite happy with the result, but anyway, it was very instructive and I think very interesting, and maybe it will interest you as well to work on a more wide scale rather than city problems. So, we start with a little bit of geography. So this is basically Irkutsk district. The city of Irkutsk is located here, or even here actually. Baikal goes like this here, and it is not shown. And it's not it's not a good picture to demonstrate transportation infrastructure of the area. But for those who are interested in details, I can provide the full-scale image. It's a PostScript file of about 25 megabytes. And you can enlarge it as much as you like, and to see all the details of this. There are two railways. One is Transsib, which goes to the east, to the southern part, and the second is the Baikal-Amur railway, which goes to the northern part of Baikal, and then further on to Komsomolsk, Na-Amuri, and Khabarovsk. And there is a number of some local links and automobile roads. And we see the clear picture later on. О, окей, Юра, ты мне время будешь отслеживать, потому что я боюсь. So this is the general statistics of this area. You see, it's rather small populated, sparse populated, only 2 million people. The car ownership is kind of an average for the Russian cities. There are about 90 settlements there. Basically, these are small villages and so on. And I didn't put, unfortunately, the road statistics on this slide, but the undevelopment of this area can be characterized by the following fact, that if you take the random location in this area and count and calculate how long is the distance from this point to the nearest road, it is on an average, it is about 30 kilometers. So if you put, in United States, this is about 1.5 kilometers. If you put random American on the, in the United States somewhere, it will take him about, I don't know, 20 minutes to come to the American highway. And here you come to something which may only remind you a road rather than a highway. So the kind of model split between different modes of transportation is the following: that the most part of the passengers flow goes to our scheduled buses. It accounts for almost 70% of the all trips. And the next is individual cars and the rail. Air is rather small because by air you travel basically to the small mining settlements in the far north of this area. We take, I can say in advance that we take this model split as kind of a fixed from the very beginning. So we didn't solve model split problem. We didn't solve it. This is more, this is schematic model for roads in Irkutsk area, and color codes are the following: that the black roads are paved roads, so it's asphalt covered. Green are kind of no unpaved roads, and red one are no roads, actually, at all. They officially do not exist, but of course they exist, and the private enterprises take people to this and these locations by using this unexisting roads. Of course, as they are unexistent, they're not taken care of, and they are in a very bad state. Funny enough that one of these roads here goes to the oldest city in Irkutsk area. This is Kiryansk, which officially doesn't have automobile communication, bus communication with the rest of the cities here. The second most important part of the transportation infrastructure is rail. which I mentioned before. This is Transsib line, and this is the BAM-Amur magistral, and there is a small branch going to Ust-Ilimsk. So there are some plans for so-called Sevsib, Northern Siberian Railway, but it goes on, and there are no definite solution where and how this rail is going to be constructed. So if you clear this, if you clear this map from unessential details, we have the following graph model for the railway station, so the railway. With imposed cars, of the automobile roads. So first we need to define the so-called correspondence matrix for this problem. That is, we have to define the number of people who are going to travel from point I to point J. And we use, as it is common in this area, a gravitational model, which consists of total volumes, which we think will go from, will leave point I, and the total number of people who are going to live in point J, and the gravitation function, which depends on some measure of distance between these two graph nodes. So we have to combine this definition of transportation matrix with some conditions, balancing conditions, and finally it comes to these balance equations for some scaling coefficients, which are the essence of this gravitational model. For that, there are a number of algorithms to balance this equations, and we use algorithm due to these authors, and it worked quite well, but not always reliable. Sometimes they do not, this algorithm does not converge, but after some changes in initial state for this algorithm, it can be done. It can converge to the balanced solution. To make a choice between different distance functions, we tried several common forms of this function, and for different ways of transportation, different functions were best. For a car, individual car traffic, the exponential form gave the best results, and for transit, rail, and to a certain extent to the air modes of transportations, the more kind of power law was the best. So after, and the scale of the problem is about 5,000 flows from point to point were defined in these calculations. After you can see from, there are some modifications of these more or less standard distance functions. For instance, it helped to introduce the attractiveness of certain nodes of this network related to the other nodes. For instance, if one node is administrative center of some region or some district, then of course people go there more often for some bureaucratic reasons, for instance. This is, and also it depends on the income at this area, which defines also the car ownership and a number of different factors. It's a kind of cross-link between purely gravitational model and so-called direct demand models, which factor traffic flows on some social economic indicators in different places on this network. Also, you can take into account the tourist traffic and things like that in this area. No, part of this work was taken for this transformation was taken from Irkutsk Office of Statistics, which is quite advanced, let's say. And here are some details for this coefficient, attractiveness coefficients. So we are not too much interested in such details, I think. Then, as I told, that this correspondence matrix was defined for the different modes of transportation. And also we did it for so-called perfect or ideal transportation network, where the graph of transportation network is a complete graph. Everybody is connected to everybody. You can go, and that kind of perfect situation. For that ideal network, we use power law as a distance function, and the following flows were obtained. And these calculations was done on a full network, so it consisted of 7,000 corresponding pairs of nodes. Then more realistic case of transportation network was computed for only 5,000 transportation flows, and such some part of this network was excluded from the consideration because it has no roads, at least official roads going to these cities. So we have no statistics on the traffic. For major part of this network, we had a little bit of data based on the sale of bus tickets from from this from people who served this this type of transportation. So individual cars were the best function for them was this distance function was exponential with a slight modification. Instead of geographic distance, we put here the time to travel from one point to another, because this time the road may consist of parts with different qualities. Some are paved, some are unpaved, and so you can move on different roads with different speeds. So it is better to put here not the geographic distance or the road distance or network distance, but the time. But the time to travel along the empty road. And for scheduled bus and rail, the power law was used with the following power in this formula. Oops, sorry. To our great surprise, the final results looked more or less like a real situation. Here, by blue, we see the computed by this modeling traffic on a certain edges of this network, for which we managed to get data. And the red were observations, real observations obtained from police, road police, from, I don't know, from many, many sources. And of course, there is a big difference in certain parts. But the general character of this dependence, red and blue dependence, is actually very similar. And this difference which take place at this parts of the network may account for the freight traffic, for moving goods and loads, some gruzy, which we, of course, did not take into account when we model passenger flow. And red was the general statistics from the road police, which just counted the number of cars which goes along this direction, not making difference with passenger cars and trucks and whatever. So we actually were quite happy with even with such correspondence between real and computed data. What the next question which we're interested in was to estimate, or to judge, to measure the quality of transportation network for this area. And for this purpose, there's a number of network indicators which shows how efficient your network is, how reliable it is, and so how convenient it is for the people. And it was done last year. We did not predict these floods in Zabaikalia regions this year, where many parts of the road traffic infrastructure in this area was damaged by floods, and it created a lot of problems. Certain cities were just isolated from the rest of the country. So I think this is very important to analyze traffic networks, especially in such undeveloped parts of the country, by some measures to have a more or less objective judgment on their structure. And also you can see which parts of the network are the most important. For instance, you calculate this index of network performance as it is, then you take some edge out of this network because of some, I don't know, reasons, natural disasters and things like that, and see how what are the changes in these indicators. And by looking at the scale of these changes, you can see which are the most important parts of your network. Also, there are a number of these network indicators which are quite, some of them are quite funny. So this probably the most kind of the oldest one, and that measure takes into account just the topology of the network. We will see how it is computed. Then Nagurno and Chang suggested generalization of this measure, which takes into account the volume of traffic which goes along the edges of the certain network. Of course, if there is an edge with a heavy load, it must be more important than some road which with the light traffic. Then there's for the networks like Irkutsk, which has very much like the tree structure. So there is basically no alternatives in going from one place to another. Then it is very important to have a look how distributed are the shortest passes on this network. And of course, the link which is used by the great number of shortest passes is, of course, more important. And so it also provides you with some interesting view of the network. And there is a generalization, of course, this indicator by some Swedes company, which also takes into account the load on these edges. And that is very interesting criteria, which was brought to my attention by, to our attention by Alexander Gaznikov, who sent me a small, pointed to the article in Science about how mold can model the roads network. Mold is plessing, or so they modeled the railway network around Tokyo by putting some foodstuff at the places where cities are on the map, and let the mold grow, and it created a network of channels between these points. and they compare it with the real railways in this area. And then they even obtained the so-called Schnobel Prize for this work, and it has a lot of follow-up papers, and if you search for the mold transportation, you will see a lot of articles on that, in saying that mold does transportation planning better than the human beings. And even there is an explanation actually for this phenomena, because these links that mold creates, they are actually like tubes, small tubes, and they pulse, pulsируют to carry food from one point to another. And if there is more food, then this tube grows, it becomes bigger, and so the network grows in the right direction. And if there is small food, then it just dies. So it has a perfect scientific explanation, and there is a different system of differential equations which describes this. So it's a kind of high tech now. Oops, pardon. Well, there's some formal definitions how we calculate these indicators. For instance, this Latour-Marchiori indicator is computed by first evaluating this sum, where this dij is a network distance from point I from node I to node j. And if graph is fully connected, the complete graph, then all these values are 1, and so this epsilon g is 1. And then we compute the similar sum, but with the lenses of edges, just summing up existing edges in this graph. And of course, for complete graph, it is the same sum. So the relation of these two values is 1. So it's a kind of a perfect traffic situation. You cannot make better than this. But for Irkutsk area, this indicator you see is kind of 10 times less than the perfect situation. So it shows you how developed is this network. And as I told you, that it shows the importance. It may be used to judge the importance of certain edges and certain nodes in this network. You just calculate this criteria for the initial network, then take node, say, take some edge out of this network, or take node out of this network with incidenting edges, recompute everything, and obtain different value for this indicator, and you see how much it changed. And the generalization due to Nagurna and Kwang has slightly different form. It uses equilibrium cost per unit of network distance. And of course, it's much more computationally intensive. You have to solve equilibrium problem to compute this indicator. And if you change your network, you have to resolve the equilibrium problem from the very beginning. So it's not heavily used as far as I know, but it's more accurate in a way. For instance, famous Bryce paradox, if you judge it by this measure, it predicted the correct negative usefulness for this parasitic edge which creates this paradox. But maybe we won't go too much into details here. And the shortest parse statistics shown here, but maybe I'll show you better the final picture. This is the graph of the road network in Irkutsk. And by red nodes are marked the most important nodes from the point of view of shortest routes. And interesting enough that Irkutsk is not the most important part of this network, but the most important are some, nobody knows, some small villages. Maybe it's on a mountain passage in the southern part of Irkutsk area or something like that. Which is often, of course, can be neglected by the transportation planners, which tend to focus on big cities and things like that. So the cost will probably yes. And then there was another question we studied, is what is the best way to make your transportation network the most insensitive or robust or resilient with respect to some natural disasters and things like that. So what should we do that to be able to serve the given transportation demand under some finite number of scenarios of natural disasters? For instance, we may know that, okay, there are floods on this river, so quite often maybe that this bridge will be damaged and not be, you cannot be able to serve it, to use it, or the capacity of this edge will be decreased by some reasons, and so on, so on. So the only way actually you can still serve the given transportation demand is to build in some redundancy in the, you have to expand some other edges of this network to carry additional load if something happens. So, but you have to do it optimally, of course, to be economically rational agents. So you can formulate it as a linear programming problem, where this is the cost of bringing in some additional capacities in the edges of this network. E is a kind of number, is index for ages. And after you build in some extra capacities, you have total capacity of this age equal to sum of the old plus 1. And then you put some measure of damage that can be caused on this age by some scenario of accidents. And you have a set of such accidents, and you have a T which numbers these accidents, and this coefficient is something like between 0 and 1 to evaluate the degree of damage. And your allowed traffic flow in this case, of course, have to satisfy this this constraint. And of course, there is a common traffic balance equations. No, so it all in all, you see there are 3 indices for variables, for the flow variables. There are expansion variables, and there are as many of them as there are ages in your network. And of course, there are a number of conservation constraints, as many as there are nodes in your network, and also for every scenario of disaster, you have different set of equations. So all in all, it comes to quite considerable large-scale problem. For instance, in the rather modest size of network with about 100 variables and 100 ages, so we have already more than 10 million of variables. So it is, but of course it is very sparse, and we are looking forward to use Nesterov's advances in this area to solve this problem. But for a while we write it down as a small AMPL, GMPL model, and use NEOS solver. Actually, it was Gurobi to solve several instances of this problem. And you see, even for it was the case just 3 scenarios for the major links going out of Irkutsk city. We may assume that they all numbered 1, 2, 3, or and there is a 0 damage scenarios, and there are 3 other cases when one of these links is broken. And even for such a small scale problem, it is already 500,000 variables, about the same size of number of constraints. So it's not very pleasant situation when you have constraints as many as variables, and the number of zeros is also quite big, but the problem is still very sparse, and it took quite a large time for even such industrial quality solver to solve, to cope with this actually not the most realistic problems. So that is the area of our further studies to decompose this problem maybe in a different way for different scenarios and things like that. And it's almost last slide. And of course, I have to have a pleasure to thank the all supporting mechanisms for this talk. How this modeling for Irkutsk area was done within this contract with the government of Irkutsk area. We have RFFI grant in this area, which just started this year, and we have 2 more years to work. And of course, it's my special pleasure to thank Prima Lab of Fistech for bringing me here. That's all. Thank you.
Do you have some time for questions?
Your model is a scholar, but passengers usually in choosing ways take into account several factors such as money cost, time cost, and reliability maybe. And maybe there is a sense to utilize vector optimization or vector equilibrium.
Yeah, definitely. But we were very limited in time and resources to do that. But now we have more or less, we can work on this, continue to work on this model with a more normal way. So there are several students working on the further development of this problem, and we of course are very much interested to do it right way.
Вот когда вы матрицу Т-жира рассчитываете, вопрос первый, у вас матрица Т-жира какой размер?
Ну вот примерно 80 на 80 где-то так вот.
80 на 80?
Да.
Потому что я считал, когда у меня было 8 тысяч на 8 тысяч,
Ну, так, конечно.
У меня вопрос такой, там, когда вы делаете калибровку,
балансировку,
дело как всегда в деталях, когда у вас в Иркутской области, у вас там появляется сумма УИТа не равна сумме дожитых, у вас 65% транзитов, да?
Да.
Это то проклятие, которое у вас будет, несмотря на примитивность структуры вот этого иркутского региона. Да? И как вот вы с этой проблемой справляетесь?
Ну, что вы имеете в виду что дисбаланс? Мы все-таки достигаем баланса в этой сети.
Так,
может быть.
То есть у вас выезжают гораздо больше, чем выезжает. Это касается и Камчатки. Поэтому там формула причет у вас вы на какой срок ее показываете?
Это годичные данные, да. Вот. Поэтому, мы считали так, что, такой сквозной трафик, он просто не учитывается. Потому что статистика вся ведется по продажам билетов. Люди, которые уезжают за пределы области, мы считали, что это отпускники, которые, в принципе, в течение года возвращаются. Вот. А такой вот миграционный общий, обезлюдивание, как сейчас говорят.
Нет, я о другом спрашиваю. У вас когда пересчет ТИЖ, у вас вот эти коэффициенты А и Б,
Да,
они
да.
пересчитывают свои куренты.
Да, да.
В такой ситуации у вас процесс разлетится, если матрица большая. Я с этим
Вы сталкивались это с вашей проблемой. Ну, у нас, видимо, не такая большая матрица, и как-то удалось все-таки...
Методический вопрос такой. Вот, вы мозг делаете в самом начале.
Да.
В принципе, надо делать по логике.
Обратно, да.
Вы сначала делаете все, потом уже модальное деление.
Да.
Но на это нужна большая задействованность.
К сожалению, нет.
В стране юга.
Да, даже это вот такое вот проклятие. Ну вот данных, вот это проклятие сейчас вот во многих областях, я думаю, транспортной тоже, оно повернется к нам другим боком. Вот. Все-таки вот система там этих сбора данных, она растет очень быстро. Вот. Значит, везде ставят эти камеры, там все, значит, базы данных. Вот. И вот, боюсь, что мы столкнемся с обратной ситуацией, и мы сталкиваемся с этим в других областях.
Когда-нибудь
слишком много данных.
Не
знаешь,
Maybe we will have this discussion after the talk, and now just the last question.
Yes, just two questions. The first one is concerning your formulation, because you take as a constraint origin and destination, and well, we know that when you change infrastructure, there is such phenomenon as induced demand, and then I was wondering if it is better to modify a little bit the approach in order to, for example, have the decision
to travel
and the decision to choose the destination, because if you improve the network, maybe you change the number of data in this network. And the second question is concerning your index. My memory is pretty bad. Laboratory.
laboratory.
Thank you. You say it's an efficiency index, but can you
In which sense?
is there economic rationale for this index?
Well, the original, but of course, you're quite right with respect to elasticity of demand, with respect to structure of network, and for that we need a little bit of different mathematics as well to formulate and to solve equilibriums. We didn't do that at that stage of the planet. And what about the Latour Marchiori? That's oriented toward the so-called small world network. It's not quite good actually for transportation networks, but still for kind of historical reasons, it was interesting to have a look at this indicator.
Okay, so let's